so using the Laplace transform to solve differential equations, that's the topic. And the trick is to see how the Laplace transform interacts with various basic operations. The last time, what we saw was that if you take the Laplace transform of a translated function, okay, so the case of C was that you translate the function to the right by C, right, by C units. If you take the Laplace transform of a translated function, then you get e to the minus cs times the Laplace transform of that function. Right? So if you take, so conversely, if you take the Laplace transform of e to the ct times the function, well, you get the translate of the Laplace transform of that function. Right? And of course, conversely, each of these has a converse statement about the inverse Laplace transform. The inverse Laplace transform of e to the minus cs f of s is of course right the Laplace transform is of course the translate by c of the inverse Laplace transform of big F of I equals s. Right? That's the same statement, I hope. And the inverse Laplace transform of a translate of some function is going to be e to the ct times the inverse Laplace transform of that function. Right? These are just the same thing twice.
What is the notation when you are multiplying by the transport out front? Does that mean that you're multiplying by the function like f of c minus, or like t minus c in the front? I'm just not really sure what it means. Are you gonna like do the Laplace transform and then do the Laplace thing and then have the transform?
So here, this is the. So if you see that you have some function translated, okay, you see that you have some function translated, and you take the inverse Laplace transform of that, well, that will be the modulation of the inverse Laplace transform of that function.
Right. I'm just wondering what the other way, like when you say like
this one?
that, going to the transform times the inverse.
Yeah. So this will be the translate of this thing. Sorry. The translate of this thing. It'll be the translate of this thing. Of the inverse Laplace transform of that. You'll see it in the following example. So to make all this clear, let's do an example. So 6.4 is basically a bunch of examples. It's just application of the above formula, and it's a bit horrendous to be honest. You have to sort of maintain your sanity through it. Because as long as you maintain your sanity, it's not difficult. Okay, so let me give. So 6.4 is basically just application of the above. So here's the example. Here is problem 2 from the homework. So you have an initial value problem, y double prime plus 2y prime plus 2y equals h of t. And the h of t is bad in the sense that h of t is going to be 1 for t between pi and 2 pi. Okay, and it's going to be 0 otherwise. So it's going to be 0 before that and after that. Right? So t looks like h looks like this between pi and 2 pi. It is 1. Right? So from here to here, it's 1. Right? And then from here onwards, and previously, it's 0. So this is what h is. Okay. So if somebody turned on a switch at a certain point, and then turned it off, turn it on at time pi, and then turned it off at time 2 pi. Okay? And that is the so-called forcing function that will affect the behavior of the solution. Okay, so we apply the Laplace transform to this. Right? So what you do, of course, is apply the Laplace transform. Right? And you get, using the book's notation, let's let y be the Laplace transform of little y. So capital Y will denote the Laplace transform. You get s squared y of s minus s little y times 0 minus y prime of 0 plus 2 s y s minus y 0 plus 2 y capital Y s equals the Laplace transform of the right hand side. Okay, and then we use our initial conditions, which I didn't write up. So the initial conditions are y0 is 0, and y prime 0 is 1. So y0 is 0, right? And y prime is 1, right? So you get s squared y plus 2sy plus 2y equals 1. I'm going to move the 1 to the other side, plus the Laplace transform of h. If you don't want to write it down, it will all be in the notes later. You can just watch if you like. Okay. So looking at this guy, h, you see, you can recognize as, well, you can think of it like this. It is, you can think of h as the function that is 1 from pi onwards, right, minus the function that is 1 from 2 pi onwards. Right? It's a difference of these characteristic functions. Right? So this guy is the guy that is 1 from pi onwards, minus the guy that is 1 from 2 pi onwards. Right? That's the notation we use.
But then how does that include the 0 to pi part of it?
Because remember, this guy is 0 before, right? This guy is 0 before. Okay. And if you take sort of an adaptive line, you can think of this as the shift of the function 1, right? The shift of the function 1, and also minus another shift of the function 1. Okay, so what happens when you take then the Laplace transform? What happens when you take the Laplace transform? Well, by our rules, we're going to get e to the minus pi s, e to the minus pi s times the Laplace transform of 1. Right, the Laplace transform of 1 was 1 over s. And we get minus e to the minus 2 pi s times the Laplace transform of 1. That's again 1 s. Right? So So this right-hand side turns into 1 plus 1 over s, e to the minus pi s minus e to the minus 2 pi s. Yeah, Christine.
Two questions. So one is way back at the end. How did you cancel those y0?
That was from here, the initial values.
Oh, okay. And then down here, how then did you get the h of t is the, what's that called again?
That's the heaviside function?
Heaviside. So how did you get that, and where's the 1? Where's the 1?
The 1 is just the function 1. You don't have to put it in if you don't want to. But h of t was this guy, right? H of t was the guy that was 1 here and then 0 onwards, right? So we're going to recognize it as a difference of two heaviside functions. We're going to say it's the guy that turns on at time pi minus the guy that turns on at time 2 pi. Right? You notice that if you take this function and subtract off the second function, you get this h function.
Okay.
So that's how you can express a function that turns on over a certain interval. Right? The heaviside function, turns on and stays on. Right? Well, a difference of heaviside functions will give you a function that turns on and then turns off.
Okay. So we took the piecewise definition of h of t and decided to represent it as that because we can do.
That's right. Because we know how to take the Laplace transform. There's an error board over the entire class. That's good. That's all right. just bear it. Or we can go ahead. Should we just go ahead? No, let's finish the problem. It's awful. I'm doing this problem mainly to illustrate how awful it is, and it will be awful. Okay, but it's useful just to see how this all works. Okay. So here we get, of course, we get y squared. So s squared plus 2s plus 2 times the Laplace transform of y is blah, right? And so y then must be 1 over s squared plus 2s plus 2 plus e to the minus pi s minus e to the minus 2 pi s 1 over s squared plus 2s plus 2. So I think as a teacher I have to resign myself to the fact that there should be an error board over the class. I'm inclined to somehow entertain you, but this is it. Okay. So at this point, you sort of know what's going to happen. This thing, you recognize, right? This is going to be some sort of shifted cosine, right? Or a shifted sine, right? This is going to be some sort of shifted sine guy, and you recognize the shift by using completing the square.
Square?
I just want to ask you this last class, but I forgot your answer. Are we going to have to memorize that whole table, or will you give the cycle?
I think I will give things like what's the Laplace transform, the cosine, the sine, this sort of thing. As for the ones that like this, however, these are more, these I think, well, I haven't decided. I may give them or may not give them. I will probably ask you to calculate some of them, right? Because just to see that you understand how to derive the formulas. Yeah.
So what exactly is s in this function?
I'm sorry?
What is s? Because s can't be 0, right?
S is the variable on the Laplace transform side. So,
Okay.
right, so like you've got you've got these functions, right? And you're looking for a function of t. You're looking for some function of t that satisfies this thing. Right? You hit this thing on Laplace transform, bring it to the Laplace transform side, the variable that we use on that side is usually called s.
Would it ever be 0?
It could be 0.
But it can't in this problem, right? Because
Right.
Was that the problem you're saying, which, because you said that there's some problem with this. Is that it? Or is that?
Well, not really, because, so, I mean, what you get is that this guy is a function, right? The Laplace transform has this form. Okay, so it's this function. It's true this function is not defined as 0, but you don't really care about that,
Okay.
right? The Laplace transform is this function, and so what we want to do is find the inverse Laplace transform of that function, even if that function is not defined as 0. Okay. And so we'll use the dictionary to find the Laplace the inverse Laplace transform of the solution. Okay. So that's not the problem. What problem? I'm not sure. I don't remember what.
I thought you said that there's some problem. You weren't sure what the answer was. I was wondering if that's what the problem was.
When you're waiting for us to ask a question, you didn't know the answer to
Yeah.
it, but none of us asked a question.
I'm sorry.
Do you remember that?
Yeah.
Yeah.
I'm sorry. Say it again.
You were waiting for us to ask a question, but none of us did, and you were like, doesn't really matter because I don't know the answer.
Oh, that's
I
right.
was wondering if that was the question.
That's not the question.
Okay.
That's not the question. You guys still haven't found the question. It's good. Because I still haven't answered it. I'm just like running ahead of you. Okay. So no, that's not the question. Okay, so let's right, this sort of thing, blah, blah, blah. Right, and then you do the partial fraction decomposition. So let me do that over here. And I'm not going to do the partial fraction decomposition. I'm just going to write down the answer. Sorry, let me. Okay, so you get that ys is 1 over s plus 1 plus e to the negative s minus e minus times the partial fraction decomposition of this thing, which turns out to be 1/2 over s. Well, let me write it like this: 1/2 of 1 over s minus 1/2 of s plus 1 plus 1 over s plus 1 squared plus 1. Okay, and the reason I'm writing it like this rather than s plus 2 on the top is because I want you to see that I want to remind myself that this is actually, you said that one of these guys is going to be the cosine and one of these guys is going to be the Laplace transform of the sine. It's going to have two parts too. Everyone on me? Question?
So your notes say how to get that.
Get the Laplace, get the
Right.
partial fraction
Yeah.
decomposition. Do you guys want to see the partial fraction decomposition?
I'm just a little bit confused about like, if you do the partial fraction decomposition 3 times, then like ultimately, in that one,
No.
you did it twice with the 1 over
Once.
s and then the larger bottom one, but then you
No.
can also split that up further.
No.
That's not partial fraction.
Okay, let me show you partial fraction decomposition in case you've forgotten. Right, you have something like this: s squared plus 2s plus 2. Right? You recognize that this thing is irreducible, right, by looking at its discriminant. Right? You see that this guy can't be reduced further over the real numbers, and so you know it's going to be something of the form a over s plus bs plus c over this. Right, that's just the rule. So it'll turn out to be something like this. Right? And then you figure out what the what A, B, and C are by multiplying through. You say, well, 1 is equal to A s squared plus 2s plus 2 plus B s squared plus CS. Just clear, just multiply through by the denominator, discuss denominator. Right? Right? And then you say, well, this is going to be A plus B s squared plus 2A plus CS plus 2A. You find the coefficients of each power of s. Okay. And then you use the identity theorem, and you say, well, the coefficient, like this is, if you want to think of it, you know, this thing on the left is a quadratic, and the thing on the right is a quadratic, and they're equal, so they must have equal coefficients. Right? So that tells us that A plus B must be 0, right? That 2A plus C must be 0, and that 2A must be 1. Right? And so A is a half, B is negative a half, right? And 2A is 1, so C is negative 1. And so you get that we get A over S plus B plus C over S squared plus 2S plus 2. So this equals that. And you factor out the minus 2, wait a second. Yep, that C should be negative 1, sorry. Negative 1. Right? And so if you factor out, and this is a half of 1 of S plus negative a half of S plus 2 over S squared plus 2S plus 2. Right, which is what we get. How many of you saw this in Calc 2 or did this in Calc 2? Okay, majority, good. Some people, I think, don't teach this, but we really need it in this class. Okay. Okay. Okay, everyone all right? Okay, so what we do, then y, then, is going to be the inverse of a cross transform of this whole thing. Okay? Okay. So let's think of this in the following pieces. We're going to divide it like this. S plus 1 squared plus 1 plus this guy minus the block. Minus this guy times the block. Should I run up there and stop it? I've done it before. thing is the shift, right, of the sine guy, right? So we know what's going to happen, right? This is the shift. This is the shift. So here's where you have to maintain your sanity. This is the shift of the Laplace transform of the sine, right? So we know what this is going to be, right? This is the c is going to be 1, right? So we get minus 1, right? So e to the minus t times the sine of t. Right? Because we're subtracting minus 1, right? We're subtracting minus 1 here.
So that's just like saying that it's the inverse Laplace transform of the t c where c equals 1 of the function s.
The c is minus 1, but yes.
Oh yeah. Oh wait.
But isn't there a negative sign in the exponent?
We're using this one.
Oh, okay.
This one's the lower one. Okay. Okay. And then we are going to get e to the, now we use the upper one, we're going to get the translation, right? The translation by pi of the inverse Laplace transform of the interior, right? The inverse Laplace transform of this, right? Well, the inverse Laplace transform of that is just 1/2 of 1, right? The inverse Laplace transform of 1 over s is 1, right? And we get minus 1/2 times the inverse Laplace transform of this thing. But remember what this thing was. This was s plus 1 over s plus 1 squared plus 1 plus 1 over s plus 1 squared plus 1, right? So that thing, the inverse Laplace transform of that is again e to the minus t times the sine guy, right? Sine plus e to the minus t times the cosine, right? Okay.
Does the cosine need the 1/2 attached to it also?
Yes.
Right, right, parentheses.
Okay. And you get the same thing for the other guy. You get minus tau sub 2 pi, same thing, 1/2 of 1 minus 1/2 e to the minus t sine t plus e to the minus t cosine t. Okay. Okay, and now let's incorporate the tau. Let's incorporate the shift. Okay. So this is going to be e to the minus t sine t plus the tau guy. Remember, you take the heaviside function. You take the heaviside function. So this is going to be 1/2 the heaviside function starting at that point. Right? Right? And then you shift the function over by pi. Right? So so we get that, and we also get minus. Right up here. So we get e to the minus 2 sine t plus the heaviside function, right, of 1/2 the heaviside function, right, because we're shifting that 1 over by pi units, right? That's, so what I've just written up is this part, right? And then we get minus 1/2 heaviside function of this thing shifted over by pi, right? So e to the negative t minus pi cosine, sine t minus pi plus e to the, again, minus t minus pi, cosine t minus pi. Right? And then you do the same thing for the other part. Right? You get minus 1/2 e plus 1/2 e to the use of 2 pi t times the guy shifted over by 2 pi. So t minus 2 pi sine t minus pi plus e to the negative t minus 2 pi cosine t minus 2 pi. And that's the answer.
And you just leave it in terms of the Heaviside function?
Yes, yes, you just leave that there. I mean, you could express it's in there. You need it there.
What is it? I guess I'm just still confused about like what it represents in a function like this, because it's just showing like where the function exists. It's kind of doing the same thing that it did.
Well, the Heaviside function is basically where there's going to be some jump in the function, right? There's going to be some, like, this basically gives a function that's described piecewise. So, you know, at time pi, this thing gets subtracted. Right? At time pi, you add, the function looks like this. Okay. But then at time pi, something gets added and something gets subtracted. Right? This new oscillating term turns on. And then at time 2 pi, something else gets turned on or turned off. Right? And that corresponds to, you know, the forcing function h. Right? Because the forcing function said you throw the switch on at pi and you turn off the switch at 2 pi. Right? And so that should be reflected. Your solution ought to be a piecewise continuous function. It must be a piecewise continuous function, right? Because of the nature of your forcing function. Right? You switch on and you turn the switch off. Right? So there's going to be a complete discontinuity of that function at those 2 points, at the on point and the off point.
Are we always going to be using this method with piecewise functions?
Yes, yes. So that's sort of the point of the Heaviside function.
So we wouldn't be doing this if it was like a continuous function?
No. Because where then the Heaviside function come into play? It wouldn't. So if you see a piecewise thing, then you know that you've got to use the Heaviside function. And in my notes I say I conclude by saying it's awful. And indeed you see it's sort of pretty awful. That's not that awful. Awful seems to be the word that I use a lot. My daughter has picked it up and she'll say, Dad, don't look, I'm going to do something really awful. And then it turns out that she put water on her hand or something like that. in the bathtub. You can see the vocabulary you use by your children, reflected in your children. My daughter often says, "What the heck? What the heck?" Recently, she started saying, "Shoot, shoot." I say that. Just to amuse you, did I tell you about like expletives, like acceptable expletives? So we were at my brother's house, and I think my sister-in-law heard me say like "shoot" or "what the heck" or something like that, and I think they don't like their son to say that, and so instead he says, what did he say? "Holy smoke." He says "holy smoke," and so I was trying to think of things I thought maybe I told you this before. I was trying to think of other things that would be acceptable, and I came up with "jumping Jiminy." Jumping Jiminy. You could say that. That's not too bad. And then my daughter was listening to us, and she started laughing and laughing, and she said, how about we say, dinosaur ate my daddy in a funny way. Dinosaur ate my daddy in a funny way. And since then, that's been like a common Okay, enough stories. Probably just not stories. Okay, so enough of that. Let's enough of translations. Let's go on to 6.5 impulses. Okay, so this is basically the Laplace transform and the Dirac delta function, which some of you may have encountered. The Dirac delta function. Okay, so we define